Okay, sorry for the delay. So, yeah, as discussed in Kuocw talk, our final exam, will be on Monday. So, let's see. So it will be on this December 17th, starting from 5 p.m., just like the usual class. And also, I'd like to remind you guys of the deadline for your term project report as well as the presentation file by the end of this week. By the end of this Sunday. Okay, so it's less than a week. 아니요? 아닌가요? 맞죠? PPT는 얘기 없었나요? 그래요? PPT는 얘기 없었어요? 근데 PPT를 좀 내줘야지 그걸 하는데.
교수님 그러면 논문이랑 PPT랑 코드랑 3개 제출해요.
네. So for the slide material, I'm sorry that I'm sorry if you haven't expected it, but it can be just a brief, composed of maybe less than 10 pages. Okay, just less than 10 pages, just to summarize what you wrote in the project report. And also we plan to have the sessions where you give a presentation about your project. Probably next, both of the classes that we will have in the next week. Any other questions?
그럼 오늘 수업까지가 거의 시험범위인가요?
시험범위요? 우리 다음 한 시간 더 있잖아요.
그러면 그거까지가 시험범위인가요?
거기서 이제 진도를 좀 못 나가면 다음 주에 조금 더 할 수도 있고요. 다음 주 월요일에. So regarding the final exam scope, this visualizing and understanding part, and also the generative models, including the GANs or generative adversarial networks, and also variational autoencoder, and some of the image translation. Those are the scope of our final exam, and the exam scope will also cover the previous contents that we studied before the midterm exam. So it will be the entire contents that we studied throughout our semester. 되게 좋아하네요. Any other questions? Okay, so let me try to quickly cover this visualizing and understanding part. So this occlusion experiment is quite simple, but it's quite effective method. Okay, so when given a full image like this, and then suppose it was classified as 95% of the elephant, and then if we just randomly hide or remove some specific regional patches, and then we see how much this probability has dropped. So when hiding this part, it was dropped into 93, and then it's like having 2% of the importance. And then if we just remove this patch next time, and then it dropped around 89, and then it means that it has the importance of 60%, right? Which indicates that the accuracy drop, right? And so this occlusion experiment is also quite widely used in not just in this machine learning, but also this deep learning tasks, but also in general machine learning. So how do you measure the importance of a particular variable? So so given like height and the weight and maybe blood type, and then suppose you trained your classifier for the diabetes of a particular person having a particular feature vector, and then suppose the classification accuracy of whether a given person having a diabetes or not is like 89%. Okay, so this is overall accuracy value. Of course, it should be for validation or the test set accuracy, and then also you can use a logistic regression or the gradient boosting tree or random forest and maybe KNN classifier and so on, right? So we can have a freedom to choose any particular classifier that we can have. And then given this setting, suppose you just removed one variable at a time, and then just do the from the training part. I mean, from the training phase, we train our model all over again by only using the two features. And then suppose the accuracy have been dropped by 89%, and then it means that this guy has the variable importance of the 6%. Okay, and in this case, suppose we remove this blood type, and then compared to this accuracy, this accuracy didn't drop almost at all. So in this case, it has only like 1% of a variable importance. Okay, so that way we can we can measure this variable importance not just in this deep learning tasks, but also in many other machine learning or general machine learning tasks. And then as the color gets darker, and it means the accuracy has dropped much or much more. Okay. And this saliency map, so the main idea is to just to pick up one single node at a particular layer, whether it is at the last layer corresponding to a particular class of dog, for example. But also we can do we can choose any internal node of maybe the third node in this fully connected layer. Okay. So once picking up that starting point, and then we just simply set the gradient of this chosen node as +1. Okay, and then do the back propagation. Okay, and then from here we don't change, although we have to do the back propagation, but we don't actually do the parameter updating on this part, but we just back propagate, basically to propagate this information about this gradient all the way to the input images pixel level. Okay, and then once we finally arrive this input layer, and then at every pixel we will have the particular gradient value, and it could be +3 and -2 and maybe +5 and so on, right? So it means it's representing basically you can intuitively think of it as kind of a sensitivity. So when selecting this pixel by the amount of +1, for example, and then the gradient at this point will be dropped by maybe -2, +3, and +5, and so on. So you can view it as kind of a sensitivity, like how sensitive this node with respect to each of our input node. And so if a particular pixel is more kind of it causes more kind of sensitivity to the output node that we chose here, and then it means that this pixel has more influence to this the target node. Okay, so that's how we kind of measure the importance with respect to each of these pixels for this chosen or given final node. Okay, so again, we can start from the output node corresponding to a particular class label, but also we can just select any given any internal node in the hidden layers. Okay, so in this case, let's see. So suppose this guy has a -5 as a pixel-wise gradient. So in this case, in this case, the meaning of it is this pixel value should decrease, right? So when it decreases, and then our target node will increase. Okay, because we set the gradient of it as +1. Okay. Okay, and then this guy, and then it should increase so that the target node can increase. Okay, so the sign is also important, right? So you can think of it as follows. So let's start from here, and then having a +1 as a starting gradient, and then suppose this pixel has a -5 for its gradient. And what does that mean? Okay, in order to make this image look more like dog, more like the dog than the current status, and then this pixel value should get darker, right? So that's the meaning. Okay, but sometimes this pixel has the gradient of +4, and then it should be brighter. Okay, but when viewing or when forming this kind of figure by using this saliency map method, then you can just use this absolute value. Okay, purely the magnitude of this sensitivity or the amount of the influence to the target node. Okay, so using this, we can do the unsupervised segmentation like this. So it's just like a kind of instant segmentation that we saw by using the mask RCNN, for example. Suppose we just obtained this detection kind of a region for this bird, and then the next step in happening in the mask RCNN is to come up with the pixel-wise segmentation that indicates this foreground objects of our interest. Okay, and then when doing this backpropagation, starting from any given hidden node or the final node, we can actually impose some of the heuristics. So although it was not explained in full detail, but let me give the brief idea about how it works. So suppose this was our forward pass. So this is one particular channel of activation map in a conv layer, and then when passing it through the value, and then those value will get killed into 0, right? And then suppose we do the backpropagation, and then arriving at this output activation channel, and then suppose this is our gradient value, right? And then when passing back through this ReLU layer, and then we just have to remember or utilize where this activation map was originally negative value, so that the output becomes 0 after as a result of the ReLU. So ReLU has this guy, right? So if it originally has this negative value, and then you guys know that the slope will get 0, right? So the gradient should be multiplied with 0. Okay, so okay, so these were the negative values, and then those gradients will get killed, right, when backpropagating through this layer, right? But this guided backprop actually adds one additional kind of heuristic. So in this case, what are the meaning of those values, okay, in terms of this activation map? So let's imagine this gradient has started from some particular node like this or like this, okay? And then yeah, it was starting with by simply setting the gradient of a chosen node as +1, okay? And then as we saw in this example about whether this pixel should be decreased or increased and how much, with the how much sensitivity, right? So you know the meaning of this, right? And then what's the meaning of this gradient values after backpropagating through the ReLU layer? So it means that, okay, even though this guy, that particular pixel of maybe -2, so this is not a RGB level pixel. So it is just an activation map arriving at this layer, okay? So in this case, for whatever meaning of this this feature or this convolutional filter, this pixel value or this activation value should be decreased so that we can increase whatever chosen node in here, right? So again, at this feature level, or yeah, whether I mean, suppose this activation map is corresponding to like detecting some kind of edges like this, okay? And then at this particular position of our image here, and then this edge should disappear, right? Because the pattern of the strength of that pattern should be decreased so that we can kind of increase the given gradient value, right? And then what about this positive value of our gradient? So it will correspond to this region in our original image, and in that case, okay, this pattern, I mean the strength of this pattern should increase so that we can, we can satisfy the given gradient of +1 at a particular chosen node. Does it make sense? Right? So in some region, for this pattern should decrease, and some region it should increase, right? And then this both like a decreasing or increasing patterns are mixed together in a single image, that may result in a little bit messy or kind of unintuitive or like a little complicated or noisy kind of a pattern at the end, right? So in this case, when doing this backpropagation, we actually also kill the negative gradient itself. So like this guy, so we don't allow like to decrease some kind of pattern at a particular position. So in this case, we just set it as 0 and set it as 0 and set it as 0. Okay, so as a result, this gradient will only have those regions that should have a kind of increased pattern of this given pattern, right? So for example, these two regions should increase the strength of this given pattern. Okay, so when doing this backpropagation, we do not allow this negative value that wants to decrease the given pattern. Okay, So this is the main idea of the guided backprop. Okay, the guided backprop. So this was just a normal backprop, but the guided backprop will just only allow the positive gradient all the way, in all of the intermediate layers. Okay, so that is the main idea. And why should it be so? There is no rigorous reason, but in practice, if you just use this positive gradient values, and then you will, empirically you will get more, cleaner kind of output. Okay. Any questions about it? Okay. So in this case, when using this guided backprop, other than just the normal backprop, we just we obtain much cleaner kind of shape of our dog, so that we can make a better sense of what particular region of our image is actually is influencing the most to the target variable, or the particular given particular node. Okay, so we can actually do this kind of whether it is a guided backprop or the backpropagation, we can actually do this process iteratively. Okay, so in this case of saliency map, let's see. So you will just do the backprop just once. Okay, just once. And then these are the gradient values, right? These are the gradient values, and their visualization is shown as follows, right? But this is just a gradient visualization, right? But it's not, we haven't actually updated our image, right? So in this case, suppose this pixel value was 105 in terms of this RGB value, and then it had a -2, and then we can simply perform the gradient descent like 0.1 and -2. Okay, so 105.2. Okay, so we will get the entirely updated after doing this one step of gradient descent that replaces or updates every pixel value in our image, right? And then we can re-evaluate, or we can do the forward propagation all the way until we reach a particular node of our interest, whether it is this node or this node, and then do the back propagation again, and then evaluate or compute the back propagation or the partial gradient with respect to every pixel that we have, and then we can obtain that image. Okay, so in this case, if you think of this process a little bit carefully, and then we update this image and then do the forward propagation, and then for the same node, same target node, and then we simply set the gradient of it as 1 and do the same thing, right? So what will be the objective function that will generate this kind of gradient? So it is a little bit kind of interesting, and also I think quite insightful kind of way of thinking. So in this case, we didn't start with any objective function in the beginning, right? We just simply set the gradient of a particular node as simply, as just a positive 1, okay? And then what will be the corresponding objective function that will always produce the gradient as positive 1. So suppose this node, suppose this node as y, for example, And then what will be the function of y that will produce the gradient at this particular node as 1. So again, so we consider this partial gradient, right? Because we are considering the gradient at this particular node, and so we have to do the partial derivative with respect to this y. Okay, so this guy should be what? 1, right? And then let's do the integral of it. And then what should be fy? It should be y, right? So in this case, we can think of as a original objective function, where we just set the gradient simply as 1 all the time. Okay, in that case, the objective function will be this guy, and I mean, yeah, you can just think of like a gradient ascent, or like using the positive sign over here. I mean, it's just a matter of flipping the sign, but it will be just like max of fy, or just max y. Okay, so in this case, when given this objective function, then the gradient will be always set as 1, and then do the backpropagation, and using that partial gradient, we will update this image. And so here, what is our variable to participate in this optimization problem? Okay. So the variable that we can carefully choose or optimize to maximize this given objective function is all the pixels that we have, not the parameter existing in our network, right? So mathematically, it can be represented as this. Our image, which has all the different pixel values. So this is not just a single scalar. It's actually a set of pixel values that we can freely and independently optimize, right? And this is our objective function. And also, in this case, this y can also be represented as like f of I, because for this output node, or this output node, it will be anyways a function of our input image, right? So it's just a mathematical kind of notation or expression. But I think it will be important for you to have the intuitive idea or understanding about what will be the objective function corresponding to the case of setting the gradient as always 1, and then what will be our variables to optimize. Okay, so that is shown here. Okay, argmax with respect to the input image, and then this fy is a particular neuron that we chose. And let's discuss about this R of an I, which is a regularizer. Okay, so so this is one example where we set this f of an I as one of the output node over here. So if it is a cat, and then we want to update this image such that its output at this node is maximized. Okay, so it is a score of this particular class that we chose, and then input parameter is I. Okay, and then what is this guy? So this is our regularizer. So far this part we understood that, right? And then what is this part? So in this case, because we have a negative sign here, so we want to minimize this part, right? We want to minimize it. And why do we want to minimize it? It is due to mainly due to like the nature or characteristic of a guided backprop. So the guided backprop, as I mentioned, all the gradient should be positive, right? Yeah, although they can be killed by the ReLU during the forward propagation of having the negative input to the ReLU, right? They will be killed. But anyways, yeah, we will not see any negative value in each of our layer, all the way through the input layer, okay? So this gradient value should be positive value at this input image, right? So in that case, what's the resulting image? So overall, any pixel will remain the same, or it will be increased by some amount because we only allow the positive gradient, right? So if you imagine like iteratively doing this gradient descent, so in this particular case, we are performing gradient ascent. But anyways, if we keep updating our images through this process, and then the overall images will get more and brighter and brighter, because we didn't allow any negative gradient, right? So we want to have this kind of regularizer so that if the total image brightness or the total square sum of this pixel value, we want to penalize that, okay? So that way we can kind of suppress this unlimited increase of every pixels that we have. Okay, and then in this particular slide, it started from this zero image, right? This zero image. So it is up to it is up to us whether we start with the zero image or a particular existing image that we have. So in this case, so we can do the same optimization process or this kind of image updating process through our gradient ascent. Yeah, starting from this particular image, okay, real existing image, or we can just start with some zero image, or maybe it can be initialized randomly, okay, from some Gaussian distribution or uniform distribution ranging from 0 to 255. Okay, so it's just a matter of initialization. So we can just start with an existing image, and then we will that will be our starting point in our optimization process, right? And then we can just start with the random initialization, right? So it's just a matter of this initialization. So if you imagine this pre-trained network, for example, in this okay, so in this case of an image captioning process, and then we have the we just bring or import this pre-trained network, and also we don't actually update this part, or we can just fine-tune that part. But in this case, we just started with the previously existing network architecture and also its own parameter set, right? So in that case, we are starting from some meaningful or already trained parameter values, and that will be our starting point. But also alternatively, we can start all the way from scratch, so that we just have a random initialization and then just train them from our image captioning model. Okay. So in practice, depending on whether we start with the random initialization or real existing image, and in the case of a random initialization or zero initialization, and then we will end up with a some of the strange image like this. Okay, but you can view it as like the optimal image that maximizes this given criteria. So in this case, the chosen target node is this one of the 1,000 classes corresponding to this dumbbell and cup and Dalmatian and things like that. Any questions so far? Okay, and then during this process, we will do a little bit additional kind of heuristics that we impose in the middle of this optimization process, such as the Gaussian blurring, and also, clip the pixels with the small values to 0 and so on. So in this case, I'm just gonna skip this part because it's just a heuristic that can improve the quality of this resulting image a little bit better. Okay, and then as I mentioned, other than just the target node, the target node at the last layer corresponding to a particular class, we can just pick up any node in the hidden layer. So we can choose any layers. And then as you can see, if you start from the later layers, and then the pattern might look much more complicated. And then if it is like a lower layer, and then the pattern seems to be much simpler compared to the previous case. Okay, let's see. Okay, so we will not cover this adversarial example generation, but there is a dedicated lecture given by the original inventor of this technique, and also Gann, whose name is Ian Goodfellow. So here, let's see. So here the main idea is as follows. Why is it called adversarial examples? Okay, so suppose you are given this image, and then this image is currently correctly classified as an African elephant. Okay, and then this image looks almost identical to the original image, but suddenly our classifier or our CNN model will classify this as maybe 99% as koala. Okay, so this is the overall kind of story. And how do we achieve this task or this goal? Okay, so let me just get back to this case. Okay, so this image is currently correctly classified as an elephant with maybe 88% of the probability. Okay, so this is the current setting, and then now we intentionally want to make or change this image so that it can classify it as the koala. So in that case, suppose the koala dimension is over here, and then it is currently having the probability as maybe only like 10%. So that is the current setting. And then now, whether setting the gradient over here, but the logit value before just the softmax. Okay, so increasing this guy will also kind of roughly the same as increasing this logit value, right? But let's just simply just choose this logit node corresponding to this koala. Okay, so let's just simply set the gradient as 1. Okay, based on our intent that the koala score is increased. Okay, and then we can imagine the same thing, and then we do the back propagation, and then suppose this image is having the gradient of +3, and this image has a gradient of -3, and this pixel has a +5 and -1, and so on. Okay, so at every pixel we will have a certain gradient value. Okay, so in this case, if we were to apply the gradient descent just in a standard manner, and then suppose this pixel value was 105, and then plus 0.1 and maybe 3. So this will be typical gradient descent, right? But suppose some pixel value has maybe the gradient of maybe 100. I mean, this is a hypothetical scenario, but suppose the gradient is really big, like 100. And then what would be the corresponding update of this pixel value? So let's say this pixel value was maybe 88, and then 0.8 times 100 will result in 98. Okay, so at the end, as a result, this pixel was changed from 88 to 98. So can we recognize it or notice it or not? I mean, if this pixel value has a higher grade, a very large value of our gradient, and then we updated it by just using the simple gradient descent, and then the difference or the amount of changes will be in proportional to the amount of the gradient, right? And then suppose these regions were mostly having the large gradient values, okay? And then after doing the gradient update, and then this part have become maybe red color. So in this case, we will easily recognize it or notice the difference, right? But here, adversarial example case, the scenario, I mean, our intent is that we just deliberately, or we just change this image with the minimum amount of difference. Okay, so the minimum amount of the difference, so that we actually don't know, we don't know it, until we carefully kind of examine it. Okay, so in this case, we can actually clip this gradient value. So if it had a gradient of 100, and then we can, I mean, as a human, when just looking at a particular image using our eye, okay, so in this image, we can think of kind of resolution of our eye, which means so have you heard about like this kind of notion of just noticeable difference? Noticeable difference. Okay. So the notion, the meaning of it is like this. So I'm gonna give you one particular color having the pixel value of 120, for example, and then I'm gonna give you another pixel or another patch or another paper that having 128. Okay. I just give you these two different colors of papers, and then I ask a person whether those two look different or not. Okay. And then in the case of humans, human eyes may not be that much sensitive, and so they may not recognize the difference between them, right? And then we add one more pixel value. I mean, we add one more pixel value difference, and more, and so on. And then the people will start to notice or recognize that difference through our human eye, right? So that minimum value is called just noticeable difference. Okay? Okay, and then this just noticeable difference has a kind of interesting characteristic and also a little bit of a kind of non-linearity. Like if it is a gray, and then people, I mean, human eyes are more sensitive to maybe some gray color rather than really white color. So in the case of pure white color, and then the noticeable difference may be a little bit larger. So in this case, we cannot increase, so we may be able to decrease this part, and then until it is decreased into 245, and then people won't be able to notify that. I mean, people won't be able to notice that, right? And also, if it is like a gray color, and then we can maybe easily notice that with these much smaller differences. So that way, this just noticeable difference is not a constant. Okay, so it is also dependent on the original color and many other circumstances. But anyways, let's just simplify, and then just noticeable difference for every pixel, regardless of its original value, is maybe 3. Okay, just 3. Okay, and then in this case, yeah, we are allowed to change this pixel value ranging between 102 and 108, right? I mean, because that is the range within just noticeable difference compared to the original value. Okay, so in this case, even though the gradient value is positive 3, which has the positive sign and also the magnitude of 3, but we at least know that this pixel value should increase so that we can increase this koala score, right? And then we can just simply set this pixel value as 108, okay? So that way, we just throw away the magnitude information and then we just take the sign of it, okay? And we just take the maximum possible value that we are allowed, which can be understood as just noticeable difference, okay? So once changing it that way, and then through this one time of this gradient descent method, then or gradient ascent method that changes this input image, and then we will get this kind of image. So here you can understand this image as having, like, for every pixel, it just it was changed with the maximum allowed amount in terms of this just noticeable difference, but whether it increased or decreased, so that is determined by the gradient descent. So the backpropagate the gradient value with respect to each of these pixels through our backpropagation. So this way of generating this adversarial examples, okay, is called, I forgot actually the name, but FG something. And FGSM. Okay, I think, yeah. Okay, yeah. So this is called the fast gradient sign method. Okay. So we only just take the sign, and also we just accelerate this image updating process through this fast gradient, meaning that we just used maximum possible magnitude of our gradient, but we only obey the sign of this computed gradient. So and also this FGSM or why our model, I mean, this can be viewed as kind of vulnerability of our model, and it can be actually used maliciously by the attacker of our deep learning based model. So suppose we just drive our car using this self-driving kind of technique. So given the vision input, it will just determine in real time whether it keeps going or turn left or right or stops. Okay, so in that case, suppose some hacker just penetrated into our car system and then replaced this image just deliberately into this, and then we won't know that. Okay, so something. I mean, we won't notice that. Something is happening over here. But in this case, with this minimum amount of the changes, it can completely mess up our system, right? So even when a person standing there, and then we can just keep going, hitting that person hard. Okay, so that is about like security and the vulnerability like issue, or hacking the neural net systems, and then how can we defend against such kind of attacks, right? So that is also quite active research area. Any questions so far? Okay, so have you understood how this deep dream works? Deep dream works. So in the case of this deep dream, so it generally follows this framework that we discussed today. So here, okay, so let me describe the main idea briefly. Okay, so we also start with some particular chosen layer. So not just a particular node, but in this deep dream case, let's just think of choosing one particular layer. And suppose we chose this layer, okay? And then through this forward propagation, we will have the activation map. And also, yeah, by the way, in this image understanding stuffs, typically this network is brought, we just bring this network as a pre-trained network. Previously trained using maybe ImageNet or any other kind of large-scale data sets. So we assume that we start with already pre-trained network. Okay, so in this case, updating these parameters in our neural net is not our concern. So we are mainly interested in updating the images, right, the pixel values. Okay, so once choosing this layer, and then we will have the first activation map and the second activation map and the third activation map and so on. And then you know the meaning of the first channel having like this kind of edge, and the second channel having maybe this kind of edge, right? Okay, and then let's bring this activation map as follows. So 1, 2, and then maybe 0, and maybe 3. And then it, of course, indicates the strength of this given pattern of this edge, for example, right? And then from here, we also arbitrarily set, or we just heuristically set the gradient corresponding to those activation values. Okay? And how? We just simply set this activation value itself as our gradient. Okay? So it means that in the case of an activation value of 2, and then we set the gradient as positive 2. And then in the case of 3, we set the gradient as positive 3. Or if we consider the activation map just before the ReLU, and then it can also involve those negative values as well, right? And so suppose this value was maybe negative 4. And then in this case, the gradient will be set as negative 4, right? Okay, so in this case, we can do the back propagation by starting from this kind of gradient values, right? And then what's the intent of it? So the intent is, for this node, we want to have the increased value of it with the amount of, in proportional to the value of 2. And then in this case, we want to increase it as well, but we want this value to be increased much more compared to this value. Because we over here, we set the gradient as 2, but in the lower, in this pixel, we set the gradient as positive 3, right? And it means that we want this value more to increase more actively, or with a larger amount. So that is the intent, right? Okay, then using this gradient with this intent in mind, we do the back propagation and change the original image. Update this image, and then we do the forward pass or the forward propagation, and then we will have the new activation value, right? And then probably this image, this one will got, yeah, we'll have updated as a 1 point maybe 2 and 2.4 and negative 4.8 and 3.6. It will not be like exact number, right? So that is the gradient, and then we don't guarantee that, yeah, we are not guaranteed to have this same kind of, I mean, same amount or the same ratio of this increasing or decreasing rate. So in practice, I mean, so my point is, if we just updated this 2 directly using the gradient, and then we may get like 0.2 as our step size, for example, and then yeah, we can have no problem of updating this 2 as 2.5 using the gradient set. But these activation values are not our variables that we can directly update, right? So the updating is only done over here, and then, yeah, hoping that this gradient can be increased by this amount, or at least in proportional to this amount, right? And so in practice, it's like 1.1 and 2.5 and 3.55 and negative 4.7, for example, right? Through our direct update of our image, right? Okay, so that was the first step, or the one step of a gradient descent, I mean gradient ascent in the deep dream. And then, given this newly updated activation map, we just set also the gradient the same as the original activation value. So here, if it is a 1.1, and then the gradient will be set as 1.1 and 2.5, and then the gradient will be set as, and things like that, okay? So in this case, let's imagine or think about the behavior of this updating scheme or strategy. Okay, so in this case, yeah, let's make it a little bit more extreme. So negative 1 and 100, or maybe 5,000 and negative 3, for example. So in this case, this will get really, really large gradient, right, in proportion to the original activation value. And this guy, which has a relatively small magnitude, and then it will get a low gradient value. Okay, so in this case, it will almost explode, right? And so this 5,000, after doing several steps of a gradient ascent, and then it may become maybe 20,000. Okay, and then in this case, maybe negative 2, and most, and this guy is maybe 300, for example. Okay, so it's like, yeah, we can view this process as like exaggerating the initially shown, or yeah, initially appearing activation value, which indicates the strength of this pattern, right? So what was the meaning of these original activation value? So that was corresponding to the strength of this particular pattern in this particular position and another position and so on, right? So that way, so starting from this image, okay? Yeah, corresponding to this region, maybe over here, right? So over here, some important pattern that will form the dog, for example. Okay, for example, dog's nose. So dog nose channel or activation map was like this, and then at this particular point, we had a relatively large activation value, right? And then through our gradient ascent done in this deep dream, and then this part will be deformed or converted in a way that the activation map corresponding to this part for this dog's nose will be more and more exaggerated. because yeah, if it had maybe 10 10 as our activation value, and then in proportion to this, and then it will be increased much more compared to the other region that didn't have any dog nose pattern corresponding to the activation value of maybe 0.1, for example, and then it will not increase that much compared to this value. So that way we will exaggerate this small kind of pattern more and more. So that's the main idea of this deep dream. Any questions? 네.
근데 그러면 이걸 왜 하는 거예요?
왜 하는 거냐고요? 목적은 그냥 재미로 하는 거예요. 네, 그냥 재미로 하는 거고. 그때 뭐 그 그로서리 스토어 보여줬죠? 그로서리 스토어. So this is the result of the deep dream, okay, and probably this. Here our input should. We initially have to specify a particular layer, and in this case, we probably set the particular layer as a little bit ladder layers, really close to the output node. Okay, so in this case, yeah. Why is it called a deep dream? So in this image, we don't see any kind of patterns, right? But from the neural net's perspective, okay, so the neural net's perspective, somewhere around here, corresponding to this part, so neural net has actually seen some of the small patterns of the dog, okay. So although we do not easily relate this part as like a dog image, but from the neural net perspective, neural net found that some of the relevant patterns with the moderate amount of the activation, okay, corresponding to the dog like a shape. So in that case, if we exaggerate what this neural net has in mind, or what this neural net sees in terms of the pattern that they see on their own, okay. In that case, if we exaggerate it, and then we can see that neural net kind of sees those kind of patterns with a kind of a small, although it is a small amount, but when exaggerating it, and then it can be shown in this, so that we can also see and understand what this deep learning or neural net sees in different parts of our image. So that's the meaning of this technique. Any other questions? So so these images, and also this image has the difference, right? So what made the difference between these different examples? It is because we chose different layers in our neural net. Okay, so in this, suppose we chose this layer to run our deep dream, and then it will try to exaggerate the patterns captured in this particular layer. But also, we can choose this layer to run our deep dream separately, right? And then, because this layer is kind of a ladder layers compared to this guy, right? And then this layer will play a role of capturing more complex patterns, right? So in that case, if we start from our deep dream starting from this layer, and then it will exaggerate relatively low level patterns like this. And also, if we start from the much later layers, which will mainly capture a little bit complicated patterns, and then it will just show this much more kind of more meaningful kind of or complete kind of shape of an object. And also, let me also discuss in this particular example, and also in the salience map cases. Once we set this target layer, and then the forward and the back prop, only need to be done within this range, right? We don't actually need to forward prop on this part because the gradient will be set in this layer that we chose, right? So the forward and the backward, that will be done within that particular, between the input image and also the chosen target layer. And also when explaining this deep dream, I just discussed about a particular, one single channel, but typically when running the deep dream, we just do this kind of deep dream kind of way of setting the gradient across all the channels within a particular layer, right? So in that case, if this edge was capturing this and this edge was capturing like this, and then we just exaggerate all together. Any other questions? So these are the deep dream pseudocode, and so the most important part is this guy. So if you just look at the deep learning library code, or if you did your homework using the NumPy to implement all the different layers, and then you will just mainly implement the forward propagation and also the back propagation, right, for a particular layer, right? So that was it. So these two modules, right? And so this is the forward propagation, the activation value. Okay, so this is the variable to store this forward propagation value, and this is the variable to store the partial gradient with respect to those variables included in that particular layer. Okay, so you can view this as a entire activation map within a particular layer, and this is the partial gradient corresponding to each pixel or each element in our entire activation map, right? And then we just it can be maybe 64 by 64 by maybe 256. So this is just typical activation map, and then this is a forward propagation activation map, and then typically when computing this partial gradient with respect to this activation map, and then we will do their own kind of computation of this back propagation, right? But in this case, we just simply assign this back propagation, the partial gradient corresponding to this activation map as the forward propagation value itself. Okay, so this is the most important main code. And for the other parts, it is a little, some additional heuristics to make this deep dream work better in practice. So like some jittering and some gradient normalization. So it's like this. So this kind of jittering is like, so we start from a single image like this, right? But just to randomize this process, we just like move this entire image by 1 pixel to the right, right? Although we have a blank column due to this shifting, but that image can be viewed as like a slight difference, slightly different version of this original image, right? So during this gradient ascent iterative processes, and then we keep kind of randomly jittering or shifting this image. And also another heuristic that we use, it's not so much about the heuristic, but it's actually quite useful technique. But okay, so this is called the L1 normalization of our gradient. So in this case, so starting from the deep dream, or starting from setting the gradient the same as activation value, and then we will do the typical backprop, and then all the way to the input pixels, right? And then suppose this pixel had the gradient of +3, and this pixel had the gradient of -3, and so on, right? And then suppose we have like the image size is a 2 by 2, and then the gradient was 3 and -1 and 5 and maybe 4. Okay, and then we can view this as like a gradient vector, like 3, -1 and 5, 4, right? And so we basically increase or decrease this gradient globally, so that the entire gradient, the gradient vector norm, or the length of this gradient vector to be always the same. So in this case, it's like 3 squared negative. So it is a L1 norm based regularization. So 3 and 1, 5 and 4, and then we divide each of these values by this amount. Okay. So in this case, we can kind of regularize this gradient ascent or gradient update at every iteration. So sometimes at a particular iteration, we may get relatively large gradient values overall. So in this case, we may change the entire image very much, right? So image may get distorted a lot, right? In that particular iteration. If our gradient is computed as really large values overall, for each of these values, right? But sometimes if these gradients are too small, and then using the one step of this gradient update, and then the image will not get changed much, right? So in this case, if we normalize this gradient with respect to it's the L1 norm, and then we can kind of we can kind of guarantee the same amount of the changes in our image overall, right? So that is the L1 norm based gradient normalization. Why do we need it? If we add it, and then it works better in practice. So that's the reason. So there is no rigorous logical reason that we should need it, but in practice, it gives a better result. Okay, so that is the gradient normalization part. And also, this gradient normalization is a quite useful technique. Let me just spend maybe 2 more minutes to just finish this explanation. So there is something called a gradient penalty. So there is a kind of regularization technique called the gradient penalty, or GP, or it is also used in GANs, training the generative adversarial network that we will study probably in the next lecture. And so in that case, suppose our gradient vector is like this kind of 4-dimensional vector. Okay, so we have our original loss function that should minimize, and also we want to have this gradient vector to always have the norm of 1. L1 unit L1 norm. Okay, so in that case, we can do this kind of heuristic that we just applied in the deep dream. So that is a kind of heuristic method, but that is not theoretically justified. But instead, kind of a more theoretically justified or cleaner strategy or technique is to actually add this as additional regularization term. So this is our gradient vector called, for example, G, and then G1 norm -1, and for example like squared, and then some parameter alpha. Okay, And then what's the role of it? So it plays a role of, like, okay, if the gradient at a particular iteration, the L1 norm based gradient was too large, okay? So in that case, the norm was 10, for example, and then it will incur, or it will just create this 9 squared as our additional loss term or loss value, right? So we don't want that situation. So in this case, the gradient, it also has its own kind of gradient or derivative, right? So yeah, it will be, it is also differentiable function, right? Like this kind of thing, right? And also maybe something like that, right? So that way, the gradient value itself can be also part of our loss function, okay, objective function, that will also give us some gradient. So that sounds a little bit ambiguous, or but if you just come up with your own example like this, and then you will get the idea. But in general, if we add this kind of loss term, and then it plays a role of like penalizing or fitting the overall gradient length or the gradient vector norm to be close to 1. Softly, right? In this case, we don't just directly or explicit normalize our gradient as an additional post-processing step that we used in the deep dream. So we don't follow that approach because that is not theoretically justified. That post-processing, where is that coming from? In our gradient descent, it doesn't include such kind of step, right? So adding that as an additional step is just a heuristic that kind of hurts the theoretical soundness of this gradient-based optimization. But in this case, we added that officially as our objective function, right? So in that case, it plays almost the same role. Okay, so I think the time's up. So let's continue this Wednesday. Okay, thank you.